So now that we've specified relations for all of the interested quantities in our weak form, we can go about starting to put together a discretization for the overall weak form. So we'll approach this term by term. We have three terms here. So we'll be considering the first one here, which is this particular term right here, which for convention reasons we call the mass matrix. This is a consequence of this approach being taken in a solid mechanics approach where time derivatives with respect to some sort of matter distribution govern the acceleration of that body. So the mass essentially represents the reluctance of that matter distribution to move. So we have an explicit formula now for our solution approximation as well as our weighting basis functions. So we can substitute this into our mass matrix. So this right here is our mass matrix. Notice that our basis functions be with respect to J. And so we'll substitute in for our solution approximation here. Now we can see we've actually broken it apart into two pieces over here. But this is this. We can see that we have our basis function times our coefficients, and we're summing them for all of our solution approximation basis functions. Now we've taken the extra step of pulling part of this sum outside of the integrand because our coefficient for any particular basis function is not a function of space, it's just a function of time. So we can happily pull this out of our integrand to simplify our integrand sum. And so here's our weighting basis function. So we've turned something that looks somewhat kind of intimidating into a little bit simpler integrand, and we have now analytical expressions for our solution bases and our weighting bases. So let's take a look at what happens when we substitute that into our integrand here. So here it is, just rewritten up top here. So we're interested in figuring out what is this quantity actually equal to. So we can substitute in our actual expressions for each of these bases, and we'll, as an example, do it with respect to the first weighting basis function, so phi sub 0. So let's also look at, to start with, psi sub 0. So both of these are 1 minus x, right? Recall that our basis functions are ramp functions. So here is, call it psi 0 and psi 1. We can see that this is the function 1 minus x, and this is the function x. So if we substitute these expressions into here, we have the integral of these two. And if we then evaluate this integral over our element, so in this case we're saying that our element ranges from 0 to 1, we can perform this big analytical integration and get an actual number out. And for the case where we have 0 and 0, this is equal to 1/3. And it's easy enough to see, right? This is going to be an x squared term, and then we're integrating that, and so it'll be some x cubed term over 3, and at 0 it'll be 0, and at 1 it will be 1 cubed is 1, so it'll be just 1/3. So now what if we were to look at the integral, again with the same weighting basis, but now we're looking at the other solution basis? Well, we can substitute that in there. So we still have our 1 minus x for our weighting basis, but now we just have an x for our approximation basis. And when we perform that integral and evaluate it from 0 to 1, we find that this is equal to 1/6. So we've done this specifically for our 0 weighting basis, but we could also do it for our one weighting basis, but we can see because these functions are the same when they have the same subscript, essentially we just get mirror images. So clearly swapping these has no effect, and clearly swapping these has no effect, so that for our one basis for our weighting, we get similar values, but they're actually swapped. So if we try to put this into some sort of matrix, so I'm going to put the integral on the outside. It's kind of an abusive notation, but here is 0, 0. Here is 1, 1. And we will follow such that our approximation ranges along the tops. That way when we multiply by a column vector for our solution coefficients, we recover our solution as required by this sum here. So here's our solution bases. So we'd like the next one to be over here. And then similarly, we have these terms. So we can see we identified when they're similar subscripts, they're equal to a third, and when they're different subscripts, they're equal to a sixth. So we get the following matrix. And notice that it's symmetric. So we can see we get from this a 2 by 2 matrix. So if the time derivative of each of the approximation coefficients, we put in a vector now, call it A prime, so that it's a little bit easier to represent notationally. And this is our mass matrix here. Then we can very succinctly write this whole shebang as just simply this. So recall this is a 2 by 2 matrix, and this is a 2 by 1 vector, and this is our solution bases direction, and this is our weighting bases. So when we evaluate this, we get out some column vector for each of the weighting bases.